Based on a lot of these features, I'm delighted to welcome Sabeel from AkerBP to share with us a case study on the ICV monitoring that was done.
I am Sabeel, as Mary mentioned, working at AkerBP in the Yggdrasil project, and I'm part of the production optimization and energy management team in pre-operations and project manager of what we call the visualization and analytics project. So we are building the operational dashboards that the production team will be using when we go live in operations in 2027. And I'm here to present a use case and POC that we've done with the team of Agen, monitoring our ICV and UCCs for Yggdrasil, but first in the POC for a brownfield asset. So just a little bit of a background on the Yggdrasil asset. It is a highly complex field with, I think it will be up to 60 wells across multiple reservoirs. So you see the reservoirs on the picture here, and I believe it's in total 10 reservoirs, 10 subsea templates, and then 3 topsides, as you see. And most of the wells will be equipped with UCCs, so that's unified control cards, gathering a tons of data from the wells, and ICVs, so interval control valves, basically be giving us pretty good control of how we let in fluid to our wells and trying to maximize the recovery of oil through multiple zones. So as of right now, we're going to have a lot of new ICV systems from Halliburton. So there will be, as of now, 18 wells equipped with the Turing ICVs, which will include more than 70 valves. We'll have 25 wells with the AkerBP ACVs. And with these, there will be several hundreds of PT gauges. So as you can see, because of the sheer size and complexity of this asset, there will be a lot of data across wells and equipment, and we only have limited time when it comes to daily analysis of the wells. We have only a limited amount of engineers that can do the analysis, so we really need to be able to get a good understanding of the whole asset in a limited amount of time. So with this POC scope for the ICV dashboards, it's basically trying to create a health monitoring and diagnostics dashboards for the ICVs mainly, but also the UCCs. So the goal is to build an understanding of the ICV systems, because these are new systems that we haven't deployed for in our assets. And we need to establish a baseline of diagnostics before we go into operations for the Yggdrasil asset. So to do this, we have done a retrofitting of a brownfield well with the Turing ICV system. And what we're trying to do is basically monitor the equipment condition using well and the UCC data, trying to get an understanding of the valves and the cards, and trying to see if there's any deviations or errors that we should look further into. And yeah, we'll try to use the learnings that we get from this POC to enable us to operate the ICVs in the best possible manner for the Yggdrasil asset. So yeah, moving a bit on, this is a schematic of the retrofitted valve for our brownfield asset. I'm not an engineer, so please forgive me if I don't know all the technical specifics, but you can't really see it really well on this schematic, but the ICVs are fitted in the different areas of the well and are basically controlling where we open and close the different valves for letting in the hydrocarbons. I wanted to show just how this will actually look for the Yggdrasil asset and in the reservoirs. So what are we trying to monitor? We're a bit unsure of what we actually should. So we have some ideas brought from the engineers. Mostly we're looking at hydraulics, pressures, and flow. These are some of the things that will probably give us the indication if something has gone wrong. But there's also other types of signals that we're looking at, such as electrical signals, powers, situations, the pressure and temperature, and see if we have some error counters for the UCC cards. But mostly, I think in this dashboard, you will see different signatures for the hydraulic pressure and rates. So this is some of the graphs and signals that showcases the operating of the hydraulic valve when it's going what we believe smoothly. This is a case where there is a leak in the system, so we see that the signature is much more erratic. And based on this, we would also like to try to find some ideal signatures for the hydraulic pressures and want to maybe benchmark those ideal signals against new events, new openings and closings and so forth. So with that, I will try to just hand it over to Miles to actually show the dashboard that we've been developing.
as Sabeel gave a really nice introduction, this is the dashboard that we've developed for the POC, monitoring a single well as a proof of concept. So this dashboard is the ICV overview. And what this dashboard is showing you is the history of ICV movements for a single well across the two ICV valves for that well. So here I've got ICV1, ICV2. Important to note before I start this that behind the scenes here, there is a ICV event engine running, which captures all of the movements live and then stores that, and then will gather any contextualized data or other information that we would want to see around that event that we can then visualize in this dashboard, such as max pressure, timing, time to open and close, different loops, the gradient, and record if there were any alarms in the UCC card or downhole gauges or the ICV itself. Let's dive into this. So this dashboard here is showing me the history for ICV1. What we capture is the time of the event. We record the well name. So the script will handle more than one well and different types of ICVs, like you said, Turing or AccuPulse, and it will handle wells with more than two ICVs going forward as well. So for each event, we classify what loop was pressurized, which ICVs moved, the initial and final position. So in this case here, it's gone from position 0 to 10. We record the max pressure during the pressurization of the hydraulic system. We then calculate the gradient of the opening and closing of the ICV. So in this case here, it's open, so it's a gradient of 0.2. I'll go into that in a second. And then we record any of the health alarms if they've flagged during the system. And then we also classify that either okay, alarm, potential interruption, or unknown. So just to run through those statuses, okay means that the signatures are what we expect. So we see a stable pressurization, we see that the ICV has moved, and then we see that a steady depressurization has happened through the return. A alarm indicates that one of the health tags has reported an alarm during that event time, and a potential interruption is the signatures look okay, but we haven't seen an ICV movement. An unknown will just capture any events that have been, the script has captured as a trigger, but it then hasn't met any of those conditions, which can then go and be analyzed further. So looking at this, we can see that the gradient for opening and closing. So why do we capture the gradient? It's because the ICV can move from either position 0 to 10, or it could go from, say, 7 to 10. So this is a normalized way of viewing the speed of opening or closing the valve. So what here we can monitor is for any degradation in the system. So looking at the opening, we can see that it's been pretty stable. There's one little anomaly here, which we can dig into, and we can see that closing has slightly increased over time, indicating that it's slightly faster. From this history table here, I can flick through the history. So any rows that are classified as alarm will be highlighted red, so the users can drill down into that. But what's great about here is that I can then look at this. I think I want to see more details around this event. So I can press this details button here. That's going to open the ICV event page, and it's going to snapshot this dashboard to the start and end of the event that we've classified here. So here we can see that the common open has pressurized. So in red, we've got the pressure. In yellow, we have the hydraulic valve position. So we can see here as that valve is opened, we see a steady pressurization. Up to about this point, we then record the max pressure. Once that's stable, then the ICV has then moved from position 0 to 10. From that, we can then see that the return valve has opened, causing a depressurization. Looking down the plots on the left here, we can also monitor the common close just to check if there are any anomalies there. We can see the return flows, and then also we can look at all of the alarm tags, which will return 0 or 1, depending on whether there was an alarm within that time. On the right here, we're showing any info. So we've got the well, the type, this case Turing, what loop was pressurized, the status, event start, end, duration. So this one took 31 minutes and 24 seconds. Here we've got some information around the position. So here we can see that the ICV1 moved from 0 to 10. ICV2 remained the same, going from 7 to 7. Looking at the pressurization, we can see the max pressure recorded was 370, and that took 20 minutes and 37 seconds. And then likewise, we can look at the return and think, okay, that took 10 minutes and 46. Like in Sabeel's presentation here, we can monitor the pressure profiles to try to detect any leaks in the system or any anomalies. From this page, I can drill into the electrical data. So this is just a simple tag showing me any electrical data around that. If I'd like to see the process graphic view of it, I can either go directly from that dashboard or I can come from the main overview. So I can click this PFD. This will open a ICV Turing template dashboard showing the hydraulic supply system and the downhole gauges. The values on the right here have been flattened, so they're not real, they're just mock for this demo. But here then, depending on how you want to see this, you could then take this dashboard, put it into live mode. At the moment, it's in a snapshot. So you can see how did that ICV movement affect your downhole gauges, pressure, and your temperature, also viewing any common alarms. From that here, engineers can then flick through the different ICVs. So if I just open ICV2, you can see that the dashboard is driven by filters. It's essentially a control group, what Denise showed. So up here, I can filter on the ICV and on different statuses. So if I just look at ICV1 and we think, okay, well, I'd like to analyze this small anomaly. So this took place on the 6th of December, 2025. So down here, I can scroll down. And typically what we can see is that when an event happens, you get a close followed by an open. However, here, what we can see is we've got a close followed by 2 opens. Analyzing that, you can see that it's gone from 10 to 0, position 0 to 7, then going from 7 to 10. I could then click on that and gain better insight to see that. So on this plot here, you can actually see the 2 movements happening within a single trend. From that, there's further data that we might want to see. So I can jump in to look at these overlay charts to detect different signatures. So here I'm able to then overlay different time periods on top of each other. So here I've got different ICV openings, and this is the tag that we calculate the gradient for. So I'm showing the ICV1 opening and closing, ICV2, and then here I can see the different pressurization profiles for pressurization and depressurization of both the open and closed loops, allowing you to see any events that have gone off and don't match the benchmark. Going forward, we will build this status panel. At the moment, obviously, we're only monitoring a single well, so the status panel isn't super useful as you can just view the history, but this dashboard will expand to be able to monitor across all 60 wells, giving you this table here will show you a row per well, giving you the well name, what system. These values here are going to give you the current status. So they're going to pull data live from the system. So you're going to get ICV health, what position you're currently running. And then from here, you can see when was something last moved. So here you've got ICV1 last moved 24 days ago, ICV2 moved 137 days ago. And then both of these are clickable. So I can then drill down into that event. And then the table below will show me ICV alarm overview the last 24 hours. So the aim of this dashboard will be that it will allow the users and the engineers to drill into only the wells that require looking into, and you don't have to go and flick through each of the wells. As well as this, if I just jump back to my overview here, the data captured in the event, we can then access it via the event log historian, which allows you to trend different integers from the event. So this chart here is not querying data from the historian, the time series historian, it's actually pulling data directly from the event. As this script expands, we'll be able to define different status classifications and different trending parameters that users would want to look into. Behind the scenes, we are running a simple Python script that is monitoring these .event tags in the system. These event tags record raw hydraulic valve movement, meaning that you don't have to process large volumes of data. If you need to do a backfill, you can just say, well, I want to query 3 years worth of data, and the only raw points one will get are valve openings or closings. That script runs in our infrastructure. We've used it many times to do very similar use cases to track blowdown valves, heat trace, gas detection. That script connects to the knowledge graph. So upon receiving that an ICV valve has changed, it can then go off to the knowledge graph, bring in contextualized data around that well that could then be stored in the event. The script then has access to all of our time series endpoints. So from that, it can use different aggregates to get max pressure within windows. We can then calculate different gradients. We can do lots of different analysis. And then that all then gets stored into a centralized events store. And then once that's stored, that data is then captured. And then in here, I'm able just to then build a standard dashboard using no custom features or components. It's just connecting to the data, just connecting to our event log data source. And then from that, I can then build up an array of different visualizations on top of that data that's captured by that analysis script.